So now I'll show you circuits that contain a voltage source as a node voltage. So let me explain what I mean by that. So we'll apply nodal analysis here as usual. So first we'll identify essential nodes. I believe this is an essential node because it's connecting the 25, the 10, and the voltage source. And I believe this is another essential node because it's also connecting 3 elements. And this one here is another essential node. So in this particular case, what I have is I have identified that this voltage source is actually connecting this essential node and this essential node, and there are no other elements in between. So this is why I mean that some circuits containing a voltage source as a node voltage. Because if I actually decided that this is actually my reference node, well, guess what? This one here is already 100 volts. I know this because I know that this here is higher than that by 100 volts because of the voltage source. So as it turns out that yes, I selected the reference node in here, but instead of having to write 2 equations at this point now, all I have to do is just write 1 equation. So all I have to do is just maybe I'll call this VA or V1, for example. That's the only voltage I need. So in order for me to solve this circuit, the only thing I need to do is just write 1 equation, figure out what the V1 is, and I'll figure out everything about this circuit. So let me write this equation. So simply this equation is, well, there's 1 node, so I just write KCL there. That equation is V1 minus 100 divided by 10. So what I did is I identified this current in here first. I said V1 minus 100 divided by 10. Okay, that's what I did. Plus, well, the second current I'm looking at is this one here, which I will say that it's simply V1 divided by 50. And then, well, the last current in here, well, it's the opposite of something I already know, which is negative 5 equals 0. And that tells me that V1 is simply I believe it is 125 volts. That's pretty much it. So I know that this is here now is 125 volts. So I know everything I need to do or to basically figure out anything else in the circuit. I will be able to figure out this current, 125 divided by 50. This current in here is pretty much 125, sorry. Let me just write that here. Okay, that current in here will be simply 125, well, I'll call it some sort of a current in here, and I'll say this is 125 minus 100 divided by 10. That will be just simply 2.5 amps. Okay, that's readily available to me. Okay, so this is just one case. If you identify that there's a source that connects 2 essential nodes, sometimes what you can do is, this is one of the choices or the better choices of the reference node. What I will do is I'll choose one of either this node or this node to be my reference point, and then I have to write 1 less equation than usual. All right, so let me show you another example. So in here, what I have is I have another circuit, and this particular time I have a circuit. Let me just do that circuit analysis on it, or nodal analysis. I'll identify the essential nodes. I believe this is an essential node, this is another essential node, and this is another essential node in here. And I believe the other ones are just simple node, not essential nodes. Okay, so what I have in here is I have the following. I have this essential node and this essential node, and what I have is I have a voltage source that connects these 2 essential nodes and nothing else. So that basically is the same as what we've done before. So if we selected one of these here, the reference point, either this point in here or this point in here as our reference point, then I will have to just write 1 equation for this particular node in here, and I'll be done. Because I know that this one here is negative 6 volts compared to the reference. For example, let's assume that I assume that this is the reference, this will be negative 6 volt. If I assume that this will be the reference, this will be plus 6 volts. Okay, so all I have to do is just write an equation for this one in here. But I'll do something a little bit different, because nodal analysis, you should be able to choose any reference point you want. It doesn't really matter. You'll just get different node voltages, but at the end of the day, the voltages across the circuit and the currents are still the same. Okay, so what I'll do is I'll just continue, and I'll, like what we've done before, and I'll select this to be my reference node. So now I have to write 2 equations for this point and this point in here. So let me call this, for example, V1, and that will be V2. And just as a quick reminder, V1 meaning this is the positive, this is the negative, V2, this is the positive, this is the negative. Okay. All right, so what I need to do right now is write 2 equations in order for me to figure out all the unknowns in the circuit and figure out, and these equations should give me what V1 and what V2 are. All right, so let's write these 2 equations. So I will start at node 1, for example. At 1, what I will do is I'll take a look at this current in here. Well, we should know that this current leaving in here, so that should be V1 minus 14 divided by 4. And now about the current going down through the 3 ohms, that will be plus V1 divided by 3. And then what about this current in here? And I'll just highlight it in pink in here so that you can see it. This current in here that is leaving. Well, I can't apply Ohm's law right now, so I can't just say V divided by R because I don't have an R. So what I need to do is I need to just say, well, it will be I, okay? And I'll just basically say plus I, because there's no other way around it. Remember, I'm applying KCL in here, just as a quick reminder. This is KCL, so it applies to currents. Yes, we need to figure out voltages, but what we're writing is KCL at these node voltages, okay? If we continue the equation here, that will be equal to 0. All right, so what I will do is I'll go back now, or I'll go again to the next node in here, and I'll say, well, let's write KCL at node B, and I'll figure out, or at node 2, and I'll figure out what to do with this I in a minute. All right, so for V2, what I'll do is I'll focus on this one in here and this one here. Frankly speaking, they're pretty much, because they're in parallel, they both have V2 divided by 6 plus V2 divided by 2. This current here is V2 divided by 6. This is this current V2 divided by 2. What about this current in here, which I'll highlight also in pink? Well, again, I can't apply Ohm's law, so I can't just say V divided by R because there's no R in here. It's a voltage source, and I don't know anything about its current. So what I'll do is I'll say, well, this is simply I, or actually it's not I because I assume that I is this way. So what do? This is just simply negative I. So what I'll do is I'll just say negative I in here, and I'll just say that this equals to 0. So what I'll do is now I'll sum up, I have 2 equations and 3 unknowns, okay? So what I will do is I'll just take this equation in here and this equation in here, and I'll just sum them. Okay, just by summing them, I'll have V1 minus 14 divided by 4 plus V1 divided by 3. Well, I'll keep that in here as positive I, okay? And then positive V2 divided by 6, positive V2 divided by 2, and then here I have negative I, and of course it equals 0. Of course, you probably have seen it now, so what I did is I eliminate the I. So all I have to do now is just remove this one here and this one here, and then we clean this up a little bit. Okay, we clean this a little bit. So this is the first equation I have in here. So, and I'll explain that in a minute. So this is equation 1. Of course, I'll have to clean it up a little bit, just isolate the V1 and V2. Okay, so let's do this here. It's 1 divided by 4 plus 1 divided by 3, and that's basically V1, plus 1 divided by 6 plus 1 divided by 2, V2 equals 14 divided by 4. And that is actually the first equation I have in terms of V1 and V2. So what I need to do is I need to go and write another equation in order for me to be able to solve this circuit. However, where would I get another equation? I already use KCL at 2 essential nodes. I use KCL in here, I use KCL in here, and what both KCLs gave me is this I in here and this I in here, but when I combine them I ended up with one equation. So I need another source for it. And what it turns out to be that if you just focus on this particular branch in here, well, I technically don't need to worry about these I's. So let me just explain. So what I can do is I can say, well, I know that V2 is just simply higher than V1 by 6 volts. So I can write this in equation, whatever I just said in equation. I can just say that V2 minus V1 should give me just 6 volts. Okay, and that turns out the equation that I'm looking for. So it's also a constrained equation because it constrained V2 to be higher than V1 by 6 volts because I have this 6 volt source in here. So all I have to do now is just write, well, my second equation is just simply V2 minus V1 equals 6. And that here is my second equation. Okay, so 2 equations. Well, I call this 2, but this should be 1 in here. Okay, so 2 equations, 2 unknowns, and I should be able to solve it. So now, what I want to show you is, yes, we can figure out what these solutions are, and you can figure out what V1 and V2 is, and I believe the answer should be, I believe V1 should be negative 0.4 volts, and then maybe V2 should be just simply 5.6 volts. Okay, let me just correct these V's. I think I use upper cases, so we'll use upper cases too. So this is V1, this is V2. But what I want to do is I want to show you a little bit of a faster way to write this equation in here. So what we have done so far is the following. We identified that this particular 2 nodes, this essential node and this essential node, has a source written across them. So what I did is I wrote the first equation, the second equation, and in both cases I got opposing currents and I added them to end up with this current. So what I will do is I'll show you a technique, and this technique will allow me will allow me to write this equation without having to go the step of writing one equation, two equations, and summing them. So I went ahead and just cleaned the figure a little bit so that we have a clean start. So what I've done here is it's the same exact circuit, and I identified the essential nodes. I decided that this is my reference node, and I decided that this will be V1 and this will be V2. So it's important to indicate that I still have two different voltages in here, and you'll see why I'm mentioning this in a minute. Okay, so our reference point in here, our V1 in here, as our V2 is in here. Okay, so of course we can directly write, well, I know what V2 minus V1, and you can just tell me V2 minus V1 is just simply 6 volts. Good, so this is your first equation. So your second equation, this is why I'm focusing on this here. We're going to do the following. We're going to do, well, look what we're going to do. We're going to just basically combine these into just big node in here. So I'm going to assume that this here is a node. What I've just done is I included the source within the node. Okay, so now I'm going to highlight it in here. So that's what we have now. And we have this here is a big node. And actually, frankly speaking, this method is called Supernode. And this is why it's called a supernode, because this is just a supernode. What we will do is we'll write KCL at the supernode. Okay, so it's KCL at the supernode. Okay, all right. So bear with me. So here, KCL at the supernode. So the whole thing is a node. So I'm going to start by saying, well, there's a current leaving it from here, a current leaving it from here, a current leaving it from here, and a current leaving it from here. So I have 4 different currents leaving this particular big supernode. Okay, so let's start with the first current in here. So the first current is going through the 4 ohms. Is simply, well, it is V1 minus 14 divided by 4. So we do the same thing we've been doing so far. We still use V1, the internal, in here. Okay, so V1 and V2, yes, they're part of this supernode, but we still use them in our equations. Okay, so we say V1 minus the 14 is divided by 4 is the first current. So what about this current in here? This current will be plus V1 divided by 3. Okay, what else do we know? Well, you ignore this current because it's part of the node now. It's internal to the node. It doesn't leave the node, the current leaving into the source, the 6-volt source. Okay, you go to the other node in here. So what do we have? We have a current leaving in here and another current leaving in here. So this current is simply V2 divided by 6 plus V2 divided by 2 ohms. Okay, and are we done? I believe the same argument goes in here. You just ignore this particular current because it's internal to the node. It just does come out. It never comes out of the node. Okay, it just goes in here to here, and that's it. It's still stuck in the node. Nothing happens there. Okay, so what we do is we just say this here equals 0, and this equation that I just wrote in here, if you scroll up a little bit, you will see that it is the same exact equation that we wrote a few seconds ago, just using these 2 methods of writing KCL at 1, KCL at 2. We use the i's in here. What I have done, and you can compare it with this one here. So this is V1 minus 14, that's the one here. V1 divided by 3, and then we have V2 divided by 6, and then V2 divided by 2, and that's 0. So this equation here is what we call a supernode. So a supernode is a node that you identify by a voltage source that connects 2 essential nodes. Okay, and if you encounter this and it just turns out to be that your reference node is not connected to one of the nodes within the supernode, you have to use this particular equation, and the second equation will be the constraint equation of the supernode, which is V2 minus V1 equals 6. And now you have 2 equations, 2 unknowns, and enjoy it. So just make sure you remember that you still have to indicate that this is V1 and you use V1, and this is V2 and you have to use V2. So if your supernode contains 2 voltages in here, just use them. You do not combine them into a single V.